Professor David Needham, the world's most significant cancer researcher. He was invited to Denmark by receiving the Niels Bohr and the Andersen professorship to proceed with his research on drug delivery. He already developed one cancer medicine, Thermodox, that successfully treats some types of cancer, and is now in the end phase of his new cancer drug.
Down in New Orleans,
I'm just focused on cancer, which has not been treated by chemotherapy or drugs effectively yet, optimized. So obviously there's some successes. The only way to treat cancer effectively 100% if it hasn't metastasized is surgery. Surgery will allow you to survive, but can we do it in a less damaging way with a simple drug that may not be that toxic but just needs delivering? Well, you can't do surgery on metastatic disease. If you get lung cancer, you can't take the lungs out.
Professor David Needham explains his first successful cancer drug, Thermodox.
So after the dog trial, we went into humans. Mm-hmm. And so the idea is that liposome with drug inside it, this is what I drew, will release the drug when it gets into the warm tumor and the drug comes out. That's the cartoon with it. So in 2007, this lady who has this cancer on her chest, so she's had the breast off and now the cancer's grown back on her chest. That's what was in that video, right? And if you heat using this device, that cancer, and put this liposome in her bloodstream, the tumor's gone. So that was the first time we saw that it would work in humans.
Chemotherapy versus Thermodox.
We can now look through a window on the of a chamber where a mouse's tumor is placed. And if you just give the chemotherapy now, doxorubicin is a chemotherapy. This is 15 minutes of heating shown in 15 seconds. So we inject the drug and then this is how long it stays there. And that's it. So the half-life is only 2 minutes for a bolus injection. The drug's gone and there's hardly anything in the tumor. That's chemotherapy, I'm sorry to say. Because you can't give so much drug that you kill the patient, but the little that you do give can't do much. So then we went to the thermosensitive liposome and we did the same thing. So now you're going to see the liposome, and the red fluorescence is the drug. The drug itself is fluorescent, so you can see it. So this is 20 minutes in 20 seconds. So the student is monitoring this with a microscope. These are real blood vessels, and the green is that liposome membrane, and the red is the drug. So now the drug is going through the whole tumor.
How to treat cancer at organs that cannot be heated and treated with Thermodox.
The academics and industry do is they just take a 60 cell, different types of cancer cells, and test as many drugs as possible on those cells. And it came out of those screens as being actually having anti-cancer activity. Who would have thought that an anti-worm drug would actually treat cancer? So the drug itself is this very old anti-worm drug. And people could take a gram of this drug. So they could take a gram every day, 1,500 milligrams or almost 2 grams, and it would kill the worm. None of it got in the bloodstream. side effects may have been gastric side effects, not feeling too well, or diarrhea or something, but it never had a systemic toxicity. So the challenge now is not to reduce the toxicity of the drug, which was the old chemotherapy way, it's to increase the delivery. So when we looked at how to formulate that drug, when he asked me, can you put it in a liposome, put it in something, we tried this technique with the drug. And what it did was, it came out of solution, but it then massively crystallized. You get lots of little fluffy crystals. I can't inject that in the bloodstream. That didn't make nanoparticles. So I had the idea of following nature's design again. What nature did with cholesterol, a very hydrophobic molecule, was make it even more hydrophobic, make it even less water soluble, by adding a hydrocarbon chain to it. That hydrocarbon chain makes it even more insoluble. When we used that compound, it worked. We got the nanoparticles. Just like if you used olive oil. You can make nanoparticles from olive oil. If you put olive oil, if you took a really good vodka and you dissolved olive oil in a very high ethanol concentration, just take 1 ml and squirt it into water, you'll get nanoparticles.
David Needham solved the delivery problem by using an endogenous method and tricking the cancer cell by hiding the drug in its food.
Now the only thing
What do fungus and bacteria eat? Because they duplicate, right? So it tends to be atoms, actually. Nitrogen, oxygen, carbon dioxide, sulfur. You know, they eat atoms, iron, in the wild. But when they infect people, they adapt and may be feeding on things that are in the bloodstream. Now we've got them, because they've adapted. The ones that are growing are surviving in the bloodstream because they're using the body's own food. Same idea. Put the drug in the bacteria's food. Put the drug in the fungus food. Put the drug in the plaque's food. Put the drug in the cancer's food. So once you understand those processes, we could treat cancer, cardiovascular disease, infectious disease. Those are the 3 biggest diseases on the planet.
How do you create the nanoparticles?
If this is a cancer cell, and there's a receptor here for a particle that is called a low density lipoprotein particle. And this protein here binds to this, and now it's in the cell. And that is its food. So if it's going to grow, it needs food. So we figured out that if that's going to happen, then this has to get there from the bloodstream anyway, and it's made in the liver. So if this is a blood vessel, and all the blood cells are going through here, like I showed, white blood cells, red blood cells, our nanoparticles are going through here, and so are the LDLs. Well, there are gaps here maybe, and they can get out. So that's one of the ways it can get out, and then the cancer eats it. So that's how we think it keeps growing. It has to feed on something to grow, right? So I said, if it feeds on the LDL, then why don't we make a nanoparticle of drug that looks just like the cancer's food? So that's the concept. So we've been in the process now of making these particles here in SDU. So the question was how to do that, because the drug comes in a bottle and it's very waxy. You can't take it orally because it doesn't go in the bloodstream very well. So it has to be injected intravenously. So now this has to go into a syringe that can be injected. So in a syringe, it has to be in a suspension of particles. Basically, we take a syringe, and in here we may put, say, ethanol or another solvent plus the drug, and then just, this is stirring, so this is going around, and this is just injected straight into here. But that's how we make the nanoparticles. So this is stirring, that goes in, and then all of a sudden we've got these nanoparticles. You can't see them because they're too small. But the process whereby we make that, and this is good because it's a little technical, we can have it on the board. If this is the size of the nanoparticle, we talk about whether something will happen depending on whether you have to put energy in to make it happen or you get energy out because it happens naturally. So when this material, this is water, when this material, ethanol, dissolves into the water, it leaves the drug to come out of solution like a precipitate. So the thing that happens is that as the particles are exchanging solvent, and if any of them get together, say you have a few molecules that come together, and then a few more molecules that come together, and a few more molecules that come together, the energy goes up to resist them coming out of solution because they have to have a surface tension against the water. So that is the resistance, and that's called the surface tension. The thing that promotes them coming together is, so now this is negative, means it helps the process, is the molecules bonding to each other. So these two curves overlap. This goes up first, and then this takes over. And so we end up with a critical size for the particle. And that size is 10 nanometers for the radius. It turns out that that size is 10 nanometers. So all of a sudden, we had a way of making the particles that were exactly the same size as the cancer's food. So the work we did here in SDU was to, with our postdocs and our graduate students, was to start here, make this, and then test it in the cell lab.
What are your next steps in this cancer drug development?
The clinical trials in dogs are the last piece of that. It's a population of dogs that are really under a lot of stress, pressure, they've got the disease. The doctors like Will Eward are trying to treat them. What he learns in the dog clinic, he can transfer to the human clinic. But if it does show efficacy in dogs, that is a clinical trial. Yeah. Then you have to prepare all the documentation and have all the tests redone. So that may take 1 to 2 years with this other company, but it could be sooner. The next stage is to scale it up in the both in volume as well as in the regulatory approval that you would need, and offer it at cost. Don't make a profit. I do not want to make a profit from this cancer treatment.
I'm going back to New Orleans, somewhere that ball and chain. Oh, oh, oh. Well, there is a house in New Orleans. They call the rising sun. And it's been a ruin for many a poor boy and dog. I know I'm one. Oh yeah, yeah. And I know I'm